Continuing with the section 3.2 notes, the multiplicity of a zero can tell us something about how the graph of the function behaves near its x-intercepts. So here's a result that we can make use of, and we'll illustrate it with some examples. Let C be a real zero of multiplicity m of a polynomial function f. If the multiplicity is odd, then the graph of f will cross through the x-axis at the point C0. That is, at x equals c on the x-axis. So if we have odd multiplicity, the graph of f will cross through the x-axis at x equals c. If m is even, if the multiplicity is even, then the graph of f will touch but not cross the x-axis at the point C0. So if we have even multiplicity, the graph will touch the x-axis at x equals c but not cross the x-axis. And then the third point would be that the greater the value of m, that is, the greater the multiplicity, the flatter the graph of f will appear near the x-intercept, near C0. Now, to illustrate some of these effects, let's look at some simple examples. We'll consider situations where 1 is a zero of multiplicity 1, 2, 3, or 4, and see how that affects the behavior of the graph near its x-intercept. An example of having 1 as a zero of multiplicity 1 is given by f of x equals x minus 1. Okay, x minus 1 is basically considered a factor in its own right. And if you want, I'll just put in some parentheses here. It's x minus 1 to the first power. 1 is a zero of multiplicity 1. So that is odd multiplicity, the smallest odd multiplicity. And what we see is that the graph just passes right through the x-axis at x equals 1. It's a straight line, notice, with a slope of 1. And it just crosses right through without any hesitation. Suppose we have f of x equals x minus 1 squared. Okay, here 1 is a zero of multiplicity 2. Its factor x minus 1 occurs twice. Now the graph is a parabola shifted 1 unit to the right so that its vertex is at 1, 0, and that vertex is an x-intercept. What do we see occurring at the x-intercept? Well, first of all, the main thing to point out is that the graph does not cross through the x-axis at x equals 1. Rather, it touches but doesn't cross. So that's the case of even multiplicity. The multiplicity here is 2, so that's even multiplicity. Now let's move to multiplicity 3. The illustration here is f of x equals x minus 1 cubed. This is a cubic polynomial, a translation of the graph of x cubed 1 unit to the right. And you can see that at x equals 1 we have an x-intercept. With odd multiplicity, we're back to the graph crossing through the x-axis as it goes through the x-intercept. It crosses through. However, we see something else. We see a flattening of the graph near x equals 1. The graph flattens out there. And so as the multiplicity increases, the graph starts to flatten out. We saw a little bit of flattening in the case of multiplicity 2. Now we see even more flattening of the graph with a multiplicity of 3. But now the graph crosses through because the multiplicity is odd. And then multiplicity 4, consider f of x equals x minus 1 to the 4th. Again, x equals 1 is an x-intercept. But now with even multiplicity, the graph is back to touching but not crossing the x-axis at x equals 1. So similar to multiplicity 2. However, you can see it does appear to be a little bit different. There is an even greater flattening effect near x equals 1. So with the greater multiplicity, with the increase in the multiplicity, we see an increased flattening in the graph as the graph approaches that particular x-intercept. Now let's consider example 3 for another example of this characteristic of the multiplicity of a zero affecting the behavior of the graph near an x-intercept. The graph of the polynomial function f is shown below. It's a computer-generated graph. Identify the zeros of f of multiplicities 1, 2, and 3. Let me organize this with a little table. So I'll have in one column the 0, and in the other column the multiplicity. There are 3 zeros we're going to identify. Going from left to right, remember zeros are associated with x-intercepts. So we have an x-intercept at -1. So -1 is a zero of this polynomial. What's its multiplicity? Well, we don't have a formula defining f, but we can look at the graph and see that the graph crosses right through the x-axis at -1. This would be associated with a zero of odd multiplicity, and since there's no flattening of the graph as it passes through -1, we'd have to assume the multiplicity is 1. The next x-intercept appears to be at x equals 0. So 0 is a zero of f. What's its multiplicity? Well, first of all, the graph touches the x-axis but does not cross at x equals 0. So that would be associated with a zero of even multiplicity. So perhaps 2, perhaps 4. The amount of flattening, well, there is a little bit of flattening there in the graph. It's kind of hard to determine whether the multiplicity might be 2 or 4. But we're going to say the multiplicity is 2 here. It's not definitive in this case. But as it turns out, when this graph was produced on the computer, the multiplicity of 0 was 2 actually. So I'm telling you the truth. It's not completely definitive just by looking at the graph. It certainly is even multiplicity, 2 or 4 probably, but in this case actually 2. And then our third x-intercept at x equals 2. So 2 is a zero of f. What's its multiplicity? Well, notice the graph crosses through the x-axis at x equals 2. As it crosses through, it flattens out. So this must be associated with a zero of odd multiplicity, most likely 3. Now, maybe it's higher than that, but it turns out again, the flattening here, it's considerably flattened as it goes through. Some of the flattening that we see here is actually a consequence of the scaling that was used to produce the graph, how much the y values are compressed or expanded as we select various ranges for the graph. So there's some distortion in the graph that makes it look flatter than it is. But actually, it was the case that when the graph was produced, the multiplicity of x equals 2 was 3. So I'm telling you the truth again. It's not definitive here because the scaling on the y-axis is not given. But we'd associate this definitely with odd multiplicity, probably multiplicity 3, possibly multiplicity 5. B says, what's the degree of f? Well, there's 2 factors to consider here. First of all, if we have listed all of the zeros of the function, then the sum of the multiplicities should always end up giving us the degree of f. If we add the multiplicities here, it's 6. So the degree of f actually is indeed 6. It's a degree 6 polynomial. The other thing to look at is the left and right behavior of the graph. To the far left and to the far left, the graph rises. We associate a graph that rises to the left and to the right with a polynomial of even degree. So this gives us more confidence that the degree is likely to be 6, since that's an even number. In fact, I can show you the actual polynomial now that produced this graph based on the zeros and their multiplicities, because the zeros are associated with factors. So our polynomial function f of x, for the 0, -1, that would be associated with the factor x plus 1, which would occur one time because the multiplicity of -1 is 1. The 0, 0 would be associated with the factor x. Since its multiplicity is 2, that factor would occur twice. And the 0, 2 would correspond to the factor x minus 2. Since its multiplicity is 3, that factor must occur 3 times. Now, the way we would usually see this written would be something like maybe x squared times x plus 1 times x minus 2 cubed. Simply rearranging the factors, that's all I'm doing there. But that actually is the polynomial that produced that graph. And another thing we could mention here is if we were to multiply this all the way out so that it's no longer in factored form, now that would be a tedious process, but it could be done. What we're saying is that by looking at the multiplicities of the various zeros, we would know that the leading term should be x to the 6th, and then there would be other terms to follow that we can't determine just by looking at the factored form. But the leading term should be x to the 6th, 6th degree polynomial with a positive leading coefficient. Again, the graph rising to the left and to the right shows us that the leading coefficient should be positive. In this case, it would be positive 1, actually. So we get all of this information from the graph. So the zeros of a polynomial function determine many of the properties or characteristics of the graph, particularly near the x-axis. That concludes the notes for section 3.2.